In this video, we're going to look at a related rates problem regarding a skateboarder who's 6 feet tall and rides under a 15-foot tall lamppost at a constant rate of 3 feet per second. We are interested in understanding how fast his shadow is changing at various points in time. So the first thing we're going to do is draw a picture of what's going on. So here's our lamppost, and here's our skateboarder. Now we're going to use x to be the distance of from the skateboarder to the lamppost, and then we're going to use s to be the shadow. Now if you look what's going on here, the tip of the shadow is going to be in a nice straight line with the tip of the skateboarder and the tip of the lamppost. The lamppost we were told was 15 feet. The skateboarder we're told was 6 feet. And now we have a situation where we see what's going on, because these are values that are changing, x and s. So what we need to do now is figure out what's going on. Well, he's moving at 3 feet per second. So if we take a look at this and figure out how it figures into our triangle, that's the rate that x is changing, because that's his distance from the lamppost. That tells us dx dt is equal to 3. Something we'll probably use later in our related rates problem. So we've got all our knowns identified, and we've got variables for our unknowns. So now we can come up with a relationship between x and s, because we have similar triangles. We have a small triangle inscribed inside another triangle. So for instance, we could say s is to 6 as, now this side is going to be s plus x, so s plus x is to 15. Okay? So 6 to 15, s to s plus x for the big triangle. Let's whittle this down to get a little bit cleaner relationship. So I'm going to go ahead and cross multiply here, and I get 15s equals 6 times s plus x, which means 15s equals 6s plus 6x, and now we'll subtract the 6s off of each side, and we get 9s equals 6x. And if we wanted to solve it for one variable or the other, maybe we'll solve it for x. We divide both sides by 6. We'll get x equals 9/6s, or I'm just going to reduce the fraction 3/2 s. So that's the relationship between x, which is the distance the skateboarder is from the lamppost, and s, the length of his shadow. Now we can use that relationship, x equals 3/2 s, to do our related rates and get the relationship between the way the rates are changing. So they take the derivative of both sides with respect to t. So the derivative of x is just dx dt. And the derivative of s, well, the constant stays, and the derivative of s is just ds dt. So this means there's a linear relationship between dx dt and ds dt, and the rate that the length of the shadow is changing is independent of where the skateboarder is at, because there's no x in this problem, or s for that matter. So in D, when they're asking for the rate that the skateboarder's shadow is changing when x is equal to 8, or when he's 8 feet from the lamppost, well, that 8 feet really didn't matter too much, because it's going to be that we know dx dt is 3 equals 3/2 ds dt. So we multiply both sides by 2/3 to cancel that out. And what we're going to get is that ds dt equals 2, because those 3's will cancel there, and our units will be feet per second. Alright. Now, as the skateboarder's distance increases from the lamppost, they want to know if his shadow's length is increasing at an increasing rate, a decreasing rate, or a constant rate. Well, as we said, it doesn't matter how far he is from the lamppost. His shadow's always going to be changing at 2 feet per second, so it's going to be constant. And as we can see, ds dt is always going to be smaller than dx dt. So for part F, we know that ds dt is always going to be smaller than dx dt. So the distance from the lamppost is going to be increasing more rapidly than the length of his shadow.